Next, we're going to take a look at transformations of exponential functions. So real quickly, as a reminder of the different types of transformations that we've already seen, if we're multiplying our function by something on the outside, that's a vertical stretch or compression. Also, if a is negative, that would be a vertical reflection, so it would flip it across the x-axis. B is the base of the function. If you look at the graphs below, if b is bigger than 1, like the example we just saw where we had 2 to the x power, the graph will grow. It will be an exponential growth. And if b is between 0 and 1, that would be exponential decay. So it would look like it's getting closer to 0 as x gets bigger. If you add or subtract something to the x in the exponent, you won't necessarily see it in parentheses, but it is grouped with the x. It's in the asylum. So it would be a horizontal shift, and it would be opposite of what you think. And finally, if you're adding or subtracting something to the end of the function, that would be a vertical shift, and it would be normal. And again, just to take a look at these graphs, depending on the different a and b value is what the graph will do. And looking at the last two, those would both be below the x-axis, so keep that in mind as well. Let's start off with some translations. Our first one is a vertical shift because we're adding 4 to the end of the function. So let's find all of our essential information. First, we've got domain. When the domain of the parent function is all real numbers, the domain of any transformation will still be all real numbers. Range depends on the vertical because y is greater than 0 for the parent function. When we shift it up 4, y will be greater than 4. Jumping down to part E, because the asymptote and the range correlate to one another, when we shift the asymptote of y equals 0 up 4, we get a new asymptote of y equals 4. So the range and the asymptote will always have that same value. One will be greater than or less than, depending on if we have a reflection, that'll be the range, and then the asymptote would be y equals. For x-intercepts, we didn't have any on the parent function, and when we shift that asymptote up and we don't have a reflection, we still will have no x-intercepts. The y-intercept also gets shifted up 4. Remember when we substituted 0 for x in the parent function, anything to the 0 power is 1. So when we add 4 to that, we get a y value of 5 or a y-intercept of 5. So here we've got the graph of the parent function for you and thinking about shifting it up 4. So first of all, our asymptote was at y equals 4. So what you want to do when you're graphing your own functions, if you don't want to graph the parent function, what you might want to do is just generate a list of a few t-chart values and use those and shift them or stretch them and then graph your new function. With the asymptote, it's nice because you don't really have to worry about negative values. You're just going to be approaching the asymptote off to the left. So really, I would just substitute -1 as my only negative exponent because the numbers get pretty small pretty quickly after that. And like I said, you can just use that asymptote to get the rest of your graph. So we would have 2 to the -1, which is 1/2. 2 to the 0 was 1. 2 to the first power is 2. And 2 squared is 4. So take all of those and shift them up 4 or add 4 to the y value. So starting with -1, we'll have 4.5. We had our y-intercept at 0, 5. For the point 1, 2, adding 4 to the y value, we get 1, 6. And adding 4 to the y value for the next point, we get 2, 8. Again, getting our curve, we would start close to that asymptote and curve up towards our other points. So comparing this graph to our parent function, we can see that it looks like it's been shifted up 4. This time we're looking at a horizontal transformation. It looks like it should be going to the left because we're subtracting. It's in the asylum, so we're actually going right 3. Starting with our domain, again, all real numbers for any exponential. For our range, because we're shifting to the right, the y equals 0 line won't shift anywhere. So we still have a range of y is greater than 0. which means jumping down to part E, our asymptote is also y equals 0. X-intercepts, because of that asymptote, we still don't have any x-intercepts. And the y-intercept, substituting 0 for x, order of operations, that -3 is grouped in the parentheses, so we should subtract the 3 before we do our exponent. 2 to the negative third power is 1 over 2 to the positive 3 power. 2 cubed is 8. So we have a y-intercept 0, 1/8. Once again, we've got the parent function graphed for us. As our asymptote is y equals 0, I'll just use that x-axis. So I'm going to take those parent function values we just generated on the last one. -1, 1/2, 0, 1, 1, 2, and 2, 4. And this time I'm going to shift them to the right 3, which means I'm going to add 3 to the x value and keep the y value the same. So my first one, adding 3 to that x value of -1, I'm going to get the 0.2, 1/2. Adding 3 to my next x value, I get the 0.31. Then I get the 0.42. And finally, I get the 0.54. To get the graph sketched using the asymptote of y equals 0 or the x-axis, and curving up towards our other points. Again, this one looks like it's been shifted to the right 3. One note with my graph here, this is a really common error that I see a lot of students make, that I just did too. It's really tempting to curve up and away from the asymptote because you know you're not supposed to cross it. It will towards the end look like it is touching the asymptote because the difference between 0 and the point is getting so small that our eyes can't see it. I would actually rather have you draw your graph on the asymptote than to curve back up like I just did, so that you can show me you know it's getting closer and closer and closer to 0.